And so you might remember last time we were talking about quadratic functions. But we're not just learning about functions because it's like, well, we're doing math for the sake of doing math. You know, historically, people weren't like, oh, I want to do abstract things because I like abstract things. They had motivations. They wanted answers to questions. And mathematics is the way that we can help get answers. That's the goal of math, is how do we get answers to questions? And so we do examples, such as the following. A company has the following functions modeling revenue and cost for given values of x. So the revenue is x times 2,000 minus 60x. And the cost is 4,000 plus 500x. And now, for which x will the company break even? They lose money, will they make a profit? And explain your answer graphically. All right. So this is a question about profit. And companies care about that number. It's sort of like the deciding, do I want to keep doing what I'm doing? So we have to think about what's going on. Now, we're not given profit, we're given revenue and cost. Okay, so how do you make profit, or how do you find profit, given those two pieces of information? Put on your beginning econ hat. What do you do? How would I figure out how much money I made if I know my revenue and if I know my cost? So you do what? Sorry?
Set it equal to each other and find out.
Well, if you set revenue equal to cost, what will that do? If your revenue equals to cost, how much have you made? Nothing. That's your break even. So break even is when your revenue equals cost. By the way, when will you lose money? When the revenue is less than your cost. And when will you make money? Well, it must be whatever's left. So revenue is more than cost. So for those of you, as a quick refresher, revenue is how much you get in. Cost is how much you have to pay out. The profit is the difference. So profit is revenue minus cost. All right, so if we're talking profit, that's revenue minus cost. So what we can do is we can make a function. We'll call it our profit function. And since these have x as our inputs, we'll make, okay, our profit is based off of x. So it's the revenue function minus the cost function. So in our case, that's x, 2,000 minus 60x. All right, so that's our revenue. Subtract 4,000 plus 500x. That's our cost. Now, on a side note, you may notice I put something in, which is the parentheses. Yes, parentheses are very useful because we're not just adding, but we're subtracting. Why do I emphasize that? Because this minus is going to come in. So parentheses are very useful to make sure you don't lose any information. So if you had put it without parentheses, you may say, oh, it's like I need to add 500x. But actually, we need to subtract it in the end. All right, well, we keep simplifying. So what do we get? Well, we get that this is equal to 2,000x minus 60x squared minus 4,000 minus 500x. And getting a little bit nervous about some of these numbers. These are some big numbers involved, but we keep going. What should we do at this stage? So we've expanded. We did our distribution. What else should we be doing? Well, we should combine terms that we can combine. We have two pieces that both have x's involved. And so I'm going to combine those. And the other thing I'm going to do simultaneously is I'm going to rewrite this in order of powers of x. So minus 60x squared plus 1500x and minus 4,000. All right. Well, what can we do? So we now have profit. So you give us a value for x, and we'll tell you how much profit we made, positive or negative. So what do we need to do to really answer our questions? Well, you say find x, but find x that does what? You're on the right track. We need to find x, but find x that's doing what? Like, what's the interesting values for x for us? Okay, so we want values that make zeros. Okay, good. So, what can we think of? On a side note, since this came from last time we talked about quadratics and parabolas, this is a quadratic because we see an x squared. Can you tell me anything about this quadratic? Well, probably you can tell me a lot of things. Let me ask you a simple one. Is this going up or down? It's going down. How do we know it's going down? Because of the negative. So our guess is it's going to look something like the following. Now, we know where it hits the y-axis. It hits at negative 4,000. That's easy because you just plug in 0. So you read off this number. So it should be doing something where it's going up, and then it's going back down. So right now we're claiming, let's try to understand these places, where we're crossing the axis. That's where profit is 0, also known as our break-even point. So we'll do some work here. Negative 60x squared plus 1500x minus 4,000 equals 0. And we start getting a little bit nervous, but that's okay. What can we do? Can we do anything to make this a little bit less intimidating? Okay, we can divide everything by 10, which basically knocks off the 0. Can we do anything else? Okay, we can divide by 2. We can even divide by negative 2 if we wanted to. So then we get 3x squared. And then it'll be minus 75x. And then it'll be a plus 200 equals 0. So I divide everything by negative 2. All right, now the next thing is, well, we gotta solve for x. And we certainly can use a calculator. That's allowed. We can also do other things. Let's see, does using a calculator help? Might be the fastest thing to do. Anybody see a way to factor this nicely? No, I'm not claiming I see a way to factor this nicely. All right. So x is equal to, or we can use quadratic formula, 75 plus or minus the square root of negative 75. So it says negative b plus or minus negative 75 squared minus 4 times 3 times 200. All of that divide by 2a, which is 6. So 75 plus or minus the square root of. That's not looking too nice. Well, this is a time when I say, well, you always have calculators. You can probably do a couple of things without calculators. Notice if we factor the 3 out, this is me if I don't have a calculator. I can just run through the similar process of completing the square. So I factor the 3 out, and this adds 625 over 2. We'll need to add 3 times 625 over 2 on the other side. So we get 3 times x minus 25 halves is equal to 3 times 625 over 2 minus 200. This is probably not any faster than using a calculator. Divide both sides by 3. Oh, this is a square I forgot to write down. X is equal to 25 halves plus or, well, okay, it's getting the same number. Did anybody have a calculator who can work this out? Sorry, I should have picked nicer numbers. Negative 75 squared, and then this will become minus 2,400.
So it's 3,225.
On the inside? 3,225. What's the square root of 3,225?
It's like 56.7.
Okay, approximately 75 plus or minus 56.
Yeah,
0.7 over 6. 75 minus 56.7. That's like 18.3 divided by 6. So I think one of our things will be about approximately 3. And another one, 75 plus 56. That's 131, almost 132. Divide that by 6. That's about 22. Okay, so that says roughly 3, roughly 22. All right, so where is our break even? At these values. Where do we make a profit? In between 3 and 22. So there's our profit. And then where do we lose money? Yeah, we lose money at the beginning, and then if we make too much. So those are where we have a loss. You could also see this graphically in a slightly different way, which is you could say, well, we have our two functions here. We have our revenue function and our cost function. In our revenue function, it happens to be an upside down parabola, and it looks something like this. This point over here is 2,000 over 60. You set this equal to 0. So there's our revenue. Then our cost looks something like this. So here's our cost function. It's a line, like mx plus b. And so, what is it you're trying to find? Your break even is where you get your intersections. That's where revenue equals cost. This part, in between, this is again profit, and then, of course, outside of that, where cost exceeds revenue, that's where you're losing money. On a side note, you might think if I'm trying to maximize profit, I should just maximize revenue. And that's not true. That's not true. You have to be careful. We could go through and actually figure out exactly where to manufacture to maximize revenue, but it turns out that's not the same as where you maximize profit. But all right, my picture's already too convoluted as it is, so we'll stop here. Sorry about being a little bit messy, but the good news is, in most situations, you'll have a calculator. So, any questions? All right. Well, where are we going? What's the goal for today? We're going to talk about two things. We're going to talk about polynomial functions. And essentially, we're just building up. We've talked about lines. Lines are polynomial functions. We've talked about quadratics. Those are polynomial functions. Just saying, hey, we can keep going. Why stop? And the other thing we'll talk about is rational functions, which look like polynomial over polynomial. Now, in both cases, things can get complicated very quickly to the point of there's some things we just can't do methodically. But we can do some very simple cases. Another thing is I like to throw in a quote. So here's today's. Comes from Abraham Lincoln, who said, "Give me 6 hours to chop down a tree, and I will spend the first 4 sharpening the axe." Which is to say, preparation is important. If you're going to jump into something, the first thing you should do is prepare. And don't underestimate the importance of preparation. You should plan for it. Set time aside, and that'll help you succeed in whatever you're trying to do. All right, so we'll start with polynomials. We've already seen examples of polynomials. We've talked about lines. We've called those linear functions. We've talked about parabolas. We call those quadratic functions. And then we just say, well, we can talk about general polynomials. We might call these nth degree polynomials. And remember, the degree refers to the power of n. So nth degree polynomials are where the highest degree is n, x to the n. And so we have to put in some notation. So these a sub whatever are the coefficients. So a sub n, you can think of this as the nth coefficient. That's attached to x to the n. And if it's nth degree, that's non-zero. Then the a sub n minus 1 just means the n minus first coefficient. That's attached to the power x to the n minus 1, all the way down to a0. So a linear function is a first degree polynomial. A quadratic is a second degree polynomial. Now, why do we want higher degrees? Well, if we have higher degrees, we can essentially get more wiggles. Our curves can do more. Now, the bad thing is, if we get higher degrees, our curves has more wiggles, and it can be hard to figure out exactly where things happen. But there are some things that we can do. We can always find the y-intercept. You plug in 0. So at least we get one freebie. Like, okay, y-intercept, we got that. We can do that. If we want to find the x-intercept, well, those are called the roots of the polynomial, and that can be hard. It's possible for anything less than degree 4 that if you give me a polynomial, there are formulas to tell the roots, but they get complicated very quickly. We know the quadratic formula, that tells us roots for degree 2. There are similar formulas for degree 3 and degree 4. There's no formula for degree 5 or higher. And we know in mathematics that no such formula can ever exist. So it's hard. The only exception is if it's given to us in factored form, because if we already have it factored, then we can take advantage of the fact that, oh, if I have a bunch of things multiplying and they're equal to 0, I just have to say when the individual pieces are equal to 0. So that's about the only time when we can find roots. Why do we like polynomials? They're nice. There's no breaks, so when you draw it, it's one line. There's no sudden where there's a sharp turn. So they're somewhat smooth. And they can model lots of behavior. Indeed, by looking at a high enough degree polynomial, you can capture almost any behavior very closely, but you have to be careful. So I use the more wiggly. Just as higher degrees, you get more ups and downs. Now, one of your questions you might face is, can I say something about a degree of a polynomial if I see just the graph of the polynomial? So here's what I mean by more wiggly. Look at the number of times you have a min or a max, right? A bottom of a bowl or a bowl turned upside down. Just count that. And then add 1 to your count. Your degree has to be at least that number. So for example, for a parabola, you've got 1 min or you have 1 max, depending upon whether it's upside down, right side up. Add 1. That means the parabola needs to have at least degree 2. The other thing is you can often say a little bit about the leading term. So that a sub n x to the n. And here's what you do. You should say, well, look, for very large values of x, the a sub n x to the n, that's the big piece. It's so big, all the other pieces will look small. So in particular, the long run behavior is driven by a sub n x n. So in the long run, for very large values of x, you say, hey, I'm basically looking like this piece. So how does that help us? Well, we can say whether or not n is odd or even, and we can say whether a sub n is positive or negative. So, if n is even, then you're either going to be going up or down at both ends. And if you say, well, okay, if n is even and a sub n is positive, then you're going to be going up for large values of x, both positive and negative. If n is even and a sub n is negative, in the long run, you're going to be going down at both ends. If n is odd, if a sub n is positive, you'll be going up for large positive values and down for large negative values. And how does that work? Well, if you take a negative number and raise it to an odd power, what happens to it? A negative number to an odd power. So I'm multiplying a negative number an odd number of times. What comes out? Stays negative. So essentially, when you have an odd power, you're not doing much to the sign. And so you say, oh, the a sub n will say whether you're still doing what you think you should do, or if you're multiplying by a sub n, which is negative, you might be flipping. On the other hand, if I have a negative to an even power, what's going to come out? Positive. And so that says the x to the n part is positive. So then I say, okay, if the a sub n is positive, then that means I have to be positive. If the a sub n is negative, I have to be negative. So by looking at the ends, you can say, oh, I can say something about the sign of a sub n. All right, so let's test these last two pieces here. So, we have some pictures below. What can we say about the minimum degree? Is the leading coefficient positive or negative? Now, I should say, you can't say definitively what the min degree is, but you can get a bound. So min degree bigger than or equal to leading term. All right, so we want to answer these questions. And we're going to do it for each one of these. Okay, so for the first one, what can we say about the minimum degree of this one? The min degree? So how many maxes or mins do we see? There's a max, there's a min, there's a max. So what's the count? How many maxes and mins? There's 3. Now what do? Add 1. So what's the min degree at least? 4. What can we say about the leading term? Positive or negative? Yeah. In fact, really, you can just look at this part right here. What's happening for large positive values? Is it going positive or negative? And so the leading term has to be negative. We do know the min degree is at least 4. We also can say, look, it has to be even. So even if it's not 4, whatever it is an even number. All right. Now that we've played it once, round 2, let's see how we do in the next one. What can we say here? What can we say about the min degree? It has to be at least 5, because we can count 4 places where we see a max or a min, add 1. Leading term, positive or negative? Negative. And we can see that whatever the min degree is, it has to be odd. It's a number at least 5, and it has to be odd. We can see that it has to be odd because there's different behavior in the 2 extremes. Same behavior at the extremes, it has to be even. All right, one more to go. What's our min degree? 6. We can count 1, 2, 3, 4, 5, and then add 1 more. Will it have to be an even or an odd? Even. So even if it's not 6, we know it definitely has to be an even number. Is the leading term positive or negative? Positive. We look and see what this is doing. It's going up. It's positive. So it's just look at what's happening on the right end. That tells you about the leading term. All right. I think that's all we have about polynomials. Any questions about polynomials? Okay. So let's switch gears slightly, and we'll talk about rational functions. So what's a rational function? There's a bit of a clue in the name. You'll see rational function starts with the word ratio. So that's like a fraction. So a rational function is formed by you take a polynomial, divide by a polynomial. So that's what a rational function is, a polynomial over a polynomial. Now, you might run into troubles because once you put a polynomial downstairs, polynomials can occasionally be 0. We call those the roots of the polynomial. And if the denominator is 0, we say, look, undefined. So there are places where the function is undefined. Essentially, those are places which we say these points are not in the domain because we can't make sense we're not allowed to divide by 0. So what are some examples? Well, you can take 3x over x squared minus 1. That's a polynomial over a polynomial. We can get a little bit more complicated. 2x plus 3x minus 5 over x squared minus 5x plus 6. But you can also do things like x squared plus 1. And you might say, wait, that's not a rational function. Where's the denominator? But it is a rational function. What is the denominator? 1. So polynomials are included inside rational functions. All right, now the question, how do we graph? Because in some sense, the graph should help us understand the behavior of the function. So how do we go about graphing rational functions? There's a couple things we can do, which are pretty straightforward. We've talked about finding y-intercepts, where we hit the y-axis. That is not so bad. Plug in 0. So if you plug 0 into your function, that says what's happening when x equals 0. X equals 0 is the y-axis. We can see where we hit the x-axis. So where we hit the x-axis is determined by the numerator. So you set p of x equal to 0. So let's see. Can we find some intercepts here? What's the x-intercept for this function, if there is any? Does this hit the x-axis? Where do we hit the x-axis at? So set the top equal to 0. When does 3x equal 0? At 0. Which, by the way, is also going to be the y-intercept. This happens to go through the origin. Maybe we can jump down to x squared plus 1. What's the x-intercept here? Yeah, there's not one. So there's a fancy symbol that we use that looks like this. I don't know, have you seen this symbol before? Do you know where it comes from? Do you know what it represents? It represents empty, right? It says there's nothing there. The fancy word is the empty set. But do you know where the symbol comes from? You think it might come from Greek. It doesn't come from the Greek alphabet. It comes from the Norwegian alphabet. This is an alphabet. It's one of the vowels. It's like, So if you're like, if I say, where's the x-intercept? You go like, and I'm like, yes, exactly. It's the empty set. Boom. Okay, well, anyways. All right. Fun facts. The other one is a little bit more tricky, but it is possible. What are the x-intercepts here? Now, I say it's a little more tricky because it's not so obvious that it factors, but it does factor. In the interest of time, I'll tell you, one of the factors is x minus 1. If I tell you one factor is x minus 1, can you tell me what the other factor is? 2x, because I need x times this to get me to 2x squared. And then minus 1 times that needs to get me to minus 5. So that's plus 5. So where are the x-intercepts? 1 and negative 5 halves. All right. Okay, so next thing, there are asymptotes. So asymptotes just says something is blowing up. Now you can blow up horizontally, you can blow up vertically. When we talk about blowing up horizontally, we're just saying in the long run, what happens? So for large values of x, does it have a particular nice behavior? Does it approach a number? So what happens for large x? So how do you figure this out? Well, what you say is for large x, we go back to the mindset we had a few minutes ago and say for large x, the behavior is dominated in a polynomial by what's in the front. So we say, okay, we're just going to channel that energy and say, ignore anything except the very front terms. So if I ignore the small stuff, for large values of x, this looks like 3x over x squared. 3x over x squared, also known as 3 over x. What's happening to 3 over x for large values of x? So 3 over x is large. What happens? It gets small. So in particular, if the degree upstairs is less than the degree downstairs, you'll have a horizontal asymptote of 0. So this one, our horizontal asymptote is 0. In particular, it's y equals 0, because we're approaching a flat horizontal line. Okay, we come here and we say, all right, ignore the small stuff. Focus on the leading terms. What does 2x squared over x squared look like? 2x squared over x squared looks like 2. And as x get big, what does 2 look like? It looks like 2. So what's our horizontal asymptote? Is 2. So when the degrees match upstairs and downstairs, you just say, oh, look at the ratio of the coefficients. So here, the degree smaller, you go to 0. The degrees are equal, look at leading coefficients. What happens here? Do we have a nice horizontal asymptote? For large values of x, what's happening to x squared plus 1? Just gets bigger. So this has no horizontal asymptote. So in particular, if the degree upstairs is bigger than the degree downstairs, there's no horizontal asymptote. It's going to get big. Now, if you took an algebra class, you may have heard of things called slant asymptotes. We're not going to go there. That's not us. All right. Now, horizontal asymptotes, what happens in the long run? There's vertical asymptotes which says, oh, the function is actually blowing up and getting huge for some particular values of x. Why could that happen? Well, because we're trying to divide by something close to 0. So essentially, our vertical asymptotes come from when does the denominator equal 0? Because if the denominator equals 0, then nearby we're trying to divide by a small thing. Dividing by a small thing is the same as trying to multiply by a huge thing. That's why we're getting big. So look downstairs. First one, does this have any vertical asymptotes? And if so, where? Yeah, because we can say when does the denominator equal 0? X squared minus 1 equals 0. At x equals 1, x equals negative 1. How about here, the next one, x squared minus 5x plus 6. Does this have any vertical asymptotes? Yeah, this factors. This is x minus 2, x minus 3. So this has vertical asymptotes at x equals 2, x equals 3. How about this last one? Does this one have a vertical asymptote? No. And by the way, you can have polynomials downstairs and not have vertical asymptotes. So for example, 1 over x squared plus 1 has no vertical asymptotes because x squared plus 1 won't be 0. Now, when it comes to graphing, you have to sort of think about how do we approach the vertical asymptote. And the answer to me is I just say, well, imagine I'm a little bit below or a little bit above. What's the sign? So we can graph some of these functions. X squared plus 1, I think we know what that looks like. Can anyone tell me what x squared plus 1 looks like? You hopefully have seen this before. All right, parabola. And we have our standard parabola. This is like our standard parabola, but we're going up, up, up. So this is x squared plus 1. All right, so that's not too interesting in some sense. Now 3x over x squared minus 1. We have a horizontal asymptote at 0 and vertical asymptotes at 1 and negative 1. So we can mark these. So we'll put minus 1, we'll put plus 1. We have a horizontal asymptote at 0, which really only kicks in for large values of x, but then we have these vertical asymptotes at minus 1 and plus 1. Now oftentimes when we mark these vertical asymptotes, we put little dotted lines. And we know we cross there at x equals 0. So how can we graph this function? Well, here's what I like to do. Imagine I'm a little bit to the right of 1. So I'm a number a little bit bigger than 1. Tell me about the signs. 3 times something a little bit bigger than 1, positive or negative? Positive. If I take something a little bit bigger than 1 and square it and then subtract 1, am I positive or negative? Positive. Which tells me I need to be positive if I'm just a little bit to the right. So that says I have to be going up because I'm positive. So I have 2 directions I could go. I could be going down or I could be going up. But follow the sign, I have to go up. But then I also know I have to approach that asymptote. And I can't cross because there's no other place that I cross. So that's my behavior here. If I'm a little bit less than 1, 0.9. 3 times that number, positive or negative? I'm positive. 0.9 squared minus 1? Negative. So what's my sign? Negative. Positive divided by negative is a negative number. So am I going up or am I going down? Going down, because it has to go down towards a negative thing. So I'm going down. So now I say, okay, I have to come here. I need to cross. Now I could just bounce back, but let's check. What happens if I'm a little bit above negative 1, like negative 0.9? Upstairs, negative. Downstairs, negative. So what's my sign? Positive, which means I need to be going up here. So I say, so I don't bounce, I cross. And finally, again, just look a little bit below negative 0.1, the sign. Upstairs, negative. Downstairs, positive. So where are we going? We're going down. So we can understand how we are approaching the vertical asymptotes by just saying, hey, look at the signs on either side. All right, I think we have enough time to try to do this one. Now, we've marked a couple of things, or we've made notes of a couple of things. We say, hey, we have an intercept at 1, so we cross. We also have, where are we at? Vertical asymptotes at 2 and 3. So here's 2. Here's 3. What else do we have? We have negative 5 halves. We cross. All right. And we have a horizontal asymptote at 2. Okay. Whew. Well, this is not the easiest one to try to figure out, but this is when factoring comes in handy. And what will happen? Well, we're going to come off go down and come through. And sorry, I know we're almost out of time. If I'm in between 2 and 3, am I positive or negative? Well, pick a number, like 2.5. Positive, 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 negative, which means it'll do this. And then if I'm bigger, it'll be positive, so it'll do something like that. So this is more complicated than what you'll be asked to draw, but I just want to say you can always do this systematically.